I really appreciated the invitation to be here, and I'm really happy to see so many of you coming to listen to this talk. It is going to be fairly personal in orientation. I have been around for a long time. I have seen a lot of exciting movements. I have seen a lot of failures. I've seen a lot of different kinds of things, and a lot of that personal experience is what is driving this presentation today. Starting off, year is 1968, and there's a horrible, horrible crisis in software. They convened a conference at NATO in Belgium, next door, to debate and to decide on how they were going to respond to this conference. So all of the best and the brightest of the computing world showed up, and they invented software engineering. So the first time that term was ever used was at this conference, and it was very controversial at the time. The nature of the crisis is interesting. There's a misperception that the crisis was crappy software. That was not really the problem. The problem was just a supply and demand problem. That computers were just starting to go into business. People were getting very excited about them. Everybody wanted them. They conferred a great strategic advantage on the people that had computers, but they didn't have anybody to write the programs. And so the crisis was not enough software developers. My first job in this profession was in 1968. I worked in a bank. We programmed an assembler in COBOL. I was the first person hired in what became the IT department that was not a banker. Our computer manager had been the operations manager at the bank for like 20 years. Everybody else in the bank, the key punchers, yes, we had to use paper cards to program our computer. The key punchers that created those cards were proof machine operators from the bank. I had to take training. Every quarter I had to do 30 hours of training in banking. Nobody cared whether or not I could write code, at least as far as background and skills and stuff go. They cared when my programs didn't run or did run. But all my training was in banking. I was a domain expert who wrote code, and that was the state of the profession. There was no such thing as a professional programmer in 1968. So in 1968, domain-driven design was basically a tautology. You were an expert writing code, so you were clearly driven by and responsive to the domain in which you were an expert. But we needed thousands of programmers tomorrow. Training a domain expert to code is quite possible, particularly with the older languages like COBOL and Fortran. It was very straightforward for a professional physicist to learn Fortran or for a banker to learn COBOL. But that's not why I was being paid. That wasn't my career path. My career path was to be president of the bank, not a programmer. So there was no way of doing that. There also was no way of training or creating this workforce of programmers at the time. There were computer science departments in major universities at the time, not a lot of them, but there were some. But they were almost exclusively math departments or electrical engineering departments. They didn't do programming. They didn't do software or software engineering. The first academic classes that became available were just language syntax classes. The idea of software engineering as a discipline with a subject matter came not until the early 70s, about 72, was when you first started seeing a lot of programs of that sort. Now, the software that was being produced by all these domain experts, it did have its problems. It wasn't the primary motivating problem for software engineering, but it tended to be idiosyncratic. And this persists. all of the software that you write is idiosyncratic. It reflects your personal style. People can go through and they can identify just by reading the code who wrote it on a team. And then the quality, of course, varied dramatically from person to person. So the idea of standardizing some of this stuff came into place. So we created software engineering, and the idea was to create a science of software development. This is one of the reasons that the whole idea of software engineering and the title was controversial, is that, number one, engineering presupposed some kind of a science, the way that every other field of engineering presupposed a science of electricity or a science of physics. So they needed a science, and they also didn't like artists. If you read all the descriptions of people that were programming in 1968, they were described as artists, not programmers, not scientists. But artists are unreliable and flaky and weird, so we don't want that in our profession. So they defined software engineering: systematic, disciplined, quantifiable approach to the development and operation of software. Systematic, mathematical, highly disciplined. So this is the objective. But it came with some consequences. First is that it just proliferated immediately. There were ways of getting students into seats in the university, so every university had to have a software engineering program. And they stuck it with, or associated it with, computer science programs where they could, or they created a computer science department in order to stick software engineering into it. The academic definitions of software and how you develop software became dominant. It didn't really matter much what people were doing or what the practice was or what practical needs were. What you wanted was provability and formalism, adherence to these kinds of standards. They also immediately, almost immediately, separated any concern of the domain from the concerns of programming. Programmers were not supposed to know anything about anything except the computer and the code. Customers would give us requirements: complete, unambiguous, accurate, up-to-date requirements. Quit laughing. It's sad, it's not funny. But they believed this, and so you as professional developers were expected to know absolutely nothing about the domains in which you were working. A kind of a long-term trend, we started to divorce, as we divorced ourselves from the domain, we also divorced ourselves from the users. In 1968, software was seen as the company's, the user's friend, and in fact, was expected to confer strategic advantage for the company that was hiring and paying them. Business loved IT. By the 70s, mid-70s, business and IT hated each other, and they entered into this long period of contractual relationship that, yes, I'll tell you what I want, but I don't expect you to understand it or give it to me. We'll ask you, the IT would ask the business, what is it that you want? But I don't believe you're ever going to tell me. And because we know we're going to fail and because we know we're going to make changes, we're going to make it as expensive as we possibly can for each other. So it was this kind of adversarial relationship. Fast forward another few years into the 90s, IT was a commodity. You're going to fail us. You're expensive. You're a commodity. You're just like electricity or rent. So we're going to get you at the cheapest possible price because the person in India isn't going to fail any worse than you are. And so we will use the people in India because they're cheaper, which is not saying anything bad about Indian programmers. They're wonderful people and they're very competent. The divergence of practice in academics. Oh, I forgot. Today, if you go and read the business press, and I don't know how many of you read the business press, which is probably your largest customer base. Do you know what they're saying about you or what they're saying about themselves or what they're trying to do? If you go and read those kinds of books from the library or the bookstore, you'll find out that the business side of the world thinks that you are an impediment, you're a barrier, you are a restriction, you hold them back. So business has been talking about being agile since the 1980s. We didn't start talking about being agile until 2000. It's not to say that there weren't objections along the way. There were a lot of them. And if you go back and you read some of the things, even some of the earliest textbooks on how to do software engineering, like Structured Analysis and Design, book that's up there, was saying that you can't focus only on the computer. You have to understand the domain, you have to model the domain, you have to figure out where and how you're going to fix it, and you're going to have to do a lot of interesting things before you sit down and write your code. Objects came along. And again, the idea was let's restructure the relationship between IT and the business, or between programmers and their customers, by at minimum giving them a common vocabulary. We'll all talk about the same set of objects and how they behave and what they do and how they interact. And then the programmers can program it and the business people can use the programs. Extreme programming was essentially a bunch of programmers saying, I'm mad as heck and I'm not going to take it anymore. They're quoting Patty Chayefsky, who used hell instead of heck. And said, look, we're professionals. We know what we're doing. Trust us. And the business said, yeah, sure. Domain-driven design came along. And again, this is a recognition of the fact that our focus was wrong. Our focus being exclusively on the machine is not helpful, is not productive. We need to understand the domain in which we are working and how it works. Design Thinking is a book that I co-wrote with a woman in Sweden. And it's attempt to pick up on a trend that already exists in the business world. You can find any number, you can find 30 or 40 books in business press about design thinking for business. You can't find very many for IT. And hopefully this will be one of the first to kind of start bridging that gap. So all of these things have been objections to the way that software engineering told us we were supposed to do. But none of them have had any lasting effect on the profession. Objects, everybody's doing objects, but nobody's doing objects as they were conceived by Alan Kay, by Rebecca, by Kent Beck, the people who really invented the whole notion or the whole idea. Agile, again, everybody probably is doing Agile officially, but they aren't doing all of Agile. They're doing parts of Agile, they're kind of Agile-ish, but more than likely they started doing extreme programming and management got upset because it wasn't under control, so they added Scrum and Lean to put it back into a more manageable kind of a process. If you're going to have a way forward, you need some prerequisites. First of all, you have to have a little bit better understanding of systems and how systems work and how you might intervene in systems. Secondly, you need to turn your back on the machine. You need to focus on the domain. And then you need an art or a discipline of living systems design. And I call it living systems design because I'm talking about doing or dealing with complex, adaptive, highly dynamic systems, which life is the most obvious example of that. Not machines, but living systems. Categorizing systems. We have natural to artificial on one axis, and we have complex to complicated on the other axis. Almost everything that we have been doing in this realm is in computational systems are very complicated, or they can be extremely complicated, and they are clearly totally artificial. The kind of systems that we need to be able to build are these ultra large scale systems down on the bottom. Systems that are not amenable to engineering. We also build a lot of hybrid systems. In fact, most of what we do are hybrid systems. The hybrid system between complicated and complex would be something like the International Space Station and the software that supports that. It works. It's been up there a long time. But it works. It's like 90%, 99% an artificial system, but it does have human beings in the space station. And human beings are complex and unpredictable. And so the only way that the space station works is by stripping every bit of humanity that you possibly can from the people that are up there, swaddling them in protocol and procedure and rules and regulations so that they have no opportunity whatsoever to do anything that a machine would not have done in the same circumstance. When things go really bad, that's when you want a human being. So Apollo 13, it was really handy that they had some humans on the spacecraft instead of just machines, because machines would have failed. Machines could not have dealt with that kind of a problem. This is kind of a generic thing that software engineering and computer science became exclusively concerned with the artificial, with the machine. And they set themselves the task of replicating reality in the machine. And they did this first by devaluing anything that made the human being different from a machine. So if you read the early artificial intelligence literature, for instance, they said that you are absolutely no different than a computer, except for the fact that you have meat instead of silicon. But you're still both physical symbol systems, you operate by the same rules, you are identical, you are one and the same thing. So there was nothing artificial about intelligence from their point of view. But the real system is not always amenable to being translated into a machine system. A machine system is deterministic. It can be very, very complicated, but it's still always deterministic. The real world is complex, does unexpected kinds of things. When you make this effort to try and recreate in the machine what exists in reality, you are setting yourself a hugely difficult task, analogous to creating the android from Star Trek or something similar. You have to replicate absolutely everything that you could or might know about human beings in some kind of an artificial medium. That's really, really hard. And most of the problems that we have in computer science and in software engineering are not intrinsic to the problem. They're intrinsic to the choice that we made to create an artificial replicant of the problem and then solve that. The patterns book that was, or the patterns, the idea of patterns that was mentioned. The first patterns book was for object-oriented programming. It was written by the Gang of Four. And it had 23 patterns that talked about how you should write code. But you could look at that book and you could say, well, these are 23 patterns for digging yourself out of the hole that you put yourself into by choosing to program in C++. It's the implementation that caused all of the problems that were being solved by the patterns, not anything intrinsic to the problems that they were trying to solve. So if you back up a little bit and start to think about a system as nothing more than a set of elements and the various relationships among them, this is a general systems theory definition of a system, very simple, very elegant. You can look at reality and say, yes, it's a complex adaptive system, living, changing constantly. If you want to understand that system, you model it in terms of its elements and the relationships among them. You model it in that sense at any level of scale. So an element in system at this level of scale can in fact be itself a system at this level of scale. So you have this kind of nested hierarchy of systems, but it's self-similar. Everything is always the same thing. You can start and think about doing design of the real system. If you conceive of reality as a set of elements and relationships and you want to alter reality to make it better, if you see your business as a set of elements and relationships and you want to enhance that business, you do so by changing one element or one relation at a time. And this kind of fact is percolated particularly through Agile with the notion of doing your unit of work being a user story, one user story, which you can complete and deliver in a couple of weeks and deploy it and get real business value from it. Design is the deliberate and intentional introduction of change into a system in order to enhance its overall state. But all of this assumes you're dealing with the real world system, not an artificial construct or an artificial replicant of that system. So the primary message of this presentation is don't do domain-driven design. That's a half step. Go and design the domain, make reality better. Don't make your program or your computer more efficient or more fun or have more blinking lights or even make it into Deep Blue and Watson that replicates the easiest kind of knowledge that there is, but go out and do domain design. So this means looking at your domain, understanding the elements. You see someone counting on their fingers, give them an abacus. It'll improve the system without making any huge changes. You can even go as far as to create a little calculator app and let them use that. It'll enhance their normal abilities. You don't do the math for them, but you give them the tool that they can use their innate human abilities to do the mathematics better and faster. If you do this, I give you a guarantee. And I see a lot of smiles as they start to read through this guarantee. However, we have instance proofs. We know that, in fact, this is true because all of these little revolutions that have occurred, we took structured analysis and design and turned it into rapid application development, which is a lot like Agile. Separate team room, whole bit. Programmers in rapid application development teams were an order of magnitude more effective than teams that were doing standard structured analysis. When we first introduced objects, and in particular objects using Smalltalk as your programming language, we demonstrated consistently that you could get this order of magnitude reduction in complexity, order of magnitude reduction in time, order of magnitude increase in quality and effectiveness and usability and enhancing the domain. You also are now in a position where you can adapt or evolve your software. If you wrote software in 1970 and used the relational database technology that was available in 1970, you were guaranteeing static operation of your business for 2 to 5 to 10 years. Guaranteeing it because it was just plain simply too costly, too difficult to change the schema in 1970. So your business was straitjacketed. We still do that all the time. Business claims to be operating in internet time, that they have to respond to challenges on a monthly basis, certainly a quarterly basis, guaranteed on an annual basis. The average time for a software project that's supposed to help this business deal with those challenges is still 2 years. So if you deliver something 2 years from now, you've already missed as many as 24 significant business-altering changes that your software doesn't support, and it also forces the business to go back and do things the way that they were doing when the project was conceived. You are doing harm. This is all very kind of superficial, so the first questions that usually come up is, aren't you forgetting these little things like data and databases and architecture and projects and project management and testing? No. If you are doing domain design and you're doing one element or one relationship at a time, the amount of code that you're going to write at any one point in time is probably less than 100 lines of code. So if that's your unit, your testing that you're testing, how much and what kind of testing do you actually need? You do need some, clearly. But it's very easy to understand how 100 lines of code are working, or 50 lines of code, whereas next to impossible to understand how 5 million lines of code are working or interacting with each other. So all of these things are addressable by doing domain design, and I haven't forgotten them. I just know that there are ways of addressing them that are not traditional. Doing this, however, presents a huge challenge, and this is the biggest reason why domain design or living system design will never happen. And I'm being cynical here, and I am not giving you enough credit. I admit right up front, I am exhibiting a kind of a negative attitude. However, starting with your skill set, it does you absolutely no good to be a master programmer if that's all that you are. You look at the design world, and one of the lessons out of design thinking is that good design and great software comes from diverse teams, people who have multiple skill sets. This has been characterized in the literature, and including some in computer software literature, starting with this notion of a T-shaped individual, that you're supposed to have someone, you're supposed to be an expert in something, but you're supposed to have some breadth as well. The design community and the business community has gone past this and saying, no, you have to at minimum be a pie-shaped individual, i.e. two areas of depth and one of breadth. Or the broken comb, multiple areas of depth. So you need to know a whole lot about a whole lot of different kinds of domains, as well as about computing. Computing can be the longest tooth in your comb, no problem with that. But if you don't know a little bit about biology, you're missing a huge opportunity of metaphors that are suggested by biology. So security is on everybody's lips these days, software security. Well, how would you go about creating a security system that mimics the body? White blood cells running around identifying invaders and taking care of them. The human immune system. There are people at the University of New Mexico that have been doing this for 5 years. And it's because they invited a biologist in to work with the team, the security team, and were able to make that bridging metaphor. In the business literature, again, you see this term modern polymath. A polymath is somebody who knows everything that there is to know. And the last person that was acknowledged to be such an individual was Leibniz in the 1800s. You obviously can't know everything that there is to know today, but you need to be this modern polymath. You need to have this breadth, this broken comb kind of ability. And that is a challenge for most people in the software world. It was a huge challenge for all of my students, the 20 years that I taught at university. Trying to get somebody to read a book that wasn't a computer book was impossible. I'm sure all of you have diverse interests in that you read, a book a month at least, and you read everything from science fiction to physics to biology, as well as the occasional computer book just for fun. You're smiling again. The second half of that challenge is, it was characterized by Kent Beck in his very first book on extreme programming. He stated that there are 3 phases to extreme programming. One is out of the book. Do what I told you, do everything I told you, do it exactly the way I told you. When you get really good at that, then you have my permission and you have the need actually to figure out how to adapt this stuff. How to modify a practice, or how to add a practice, or delete a practice from what it is that you are doing to your own current situation. The step 3 is transcendence. This is the step where you are no longer doing it by the book, or by rules, or by formulas. You're just doing it because you automatically recognize and act in the correct way. This is the meaning of Satori, is correct action at every minute of your life. And it assumes omniscience, of course, in Zen. But modern polymath is as close as you're going to get. But the idea is to transcend what it is that you're doing. Sesshu wrote this scroll. It's a series of landscapes, 14 inches high, 50 feet long. And it's all ink drawings of landscapes. Those are 2 panels from this scroll. And he painted it in a single afternoon of his 89th year on a sunny day on the mountain. He was in the zone. He had transcended painting. He had, the conceptualization or the observation of nature, probably the conceptualization from a lot of exposure and experience to doing this. And so he sat down and he just let the brush go, primarily of his own volition. We see this in other areas too, and we acknowledge this kind of potential of human beings. Athletes who get in the zone. Michael Jordan scoring 100 points. I mean, he can't do anything wrong, but he's not thinking about anything. He's just responding to a perfect knowledge of the situation and scoring. I have seen people writing code, a couple thousand lines of code in an hour and a half, 2 hours, something like that. It's perfect. It's flawless. It has no bugs. I have seen it done. I know it can be done. There's a whole human potential movement out there, which I won't get into, but it's possible. But is it something that you want? Something that you are willing to do? If you really, really want to be an expert at your profession, if you really want to be a group of people who are going to make the world a better place, you need to have that kind of breadth of knowledge and skills and be able to start transcending them at some point. This is just advertising, blog and website and the book that I just finished writing. So that's it. We are now open for questions. And I tried to go through this very fast so that there would be a lot of questions. I tried very hard to make you angry, or to at least provoke, responses. So hopefully there will be a lot of questions.
So when you're talking about complex adaptive systems, in my experience, they have 4 characteristics. They're self-organizing, they're emergent, they have the chaos order dynamics, and I can't remember the 4th one right now. But what's your point, what's your position in, should software or computational systems evolve into the same thing? Should they also be self-organizing? Should they also be self-emergent? So that at some point, the computational systems will evolve together with the real systems that evolve around them.
Yes and no.
It depends.
I would say that it would be a good thing if software could be evolvable or could be complex. Recognize all of these characteristics of complex systems like emergence and so on. However, I do not see a path to that possibility in front of me, except in systems that people are building that are extremely distributed. So if you look at agent-based modeling and agent-based systems, they have the potential at least to become complex. If you look at SAP kinds of systems, there isn't a prayer. The kind of hierarchical command control systems that we have been building for 50 years, there's no way that they're going to evolve to be complex. They'll get more and more complicated, but they'll never become complex. So yes, it would be nice, and there are some approaches that may get us there, but not real soon. The real point of looking at complex systems is to make the distinction between, if I'm doing a deterministic system, a machine, in principle, I can know every single element, I can know every single relationship, and I can quantify them. In a complex system, that's not possible. You not only do not know an element or a variable, you can't know. Solutions change the system in such a way that it redefines the problem that you were trying to solve. So if you want to deal with complex systems, you need to learn a different set of skills. And that's what the design thinking book is about, is what set of skills allow you to confront and attack ambiguity, complexity, the change that was advocated by Kent Beck, or even the understanding your domain as a domain.
So I was just wondering, have you reached this level of transience that you're talking about?
You never ask a guru if he's enlightened. I started studying Asian philosophy also in 1968. So I was a student at Macalester College, and I was going to be a quantum physicist. And I found physics so boring that I switched to Asian philosophy. So I have been studying these various kinds of things with Buddhism in China, to Japan, to the US, for a long, long, long time. And that's the most I will say.
So, as one of the later points of your presentation, you're saying that, okay, but we'll probably never get there, right? And then you had some points on, stuff that should be in place. If there's one thing, you see this. We are missing. I don't read biology books that often. My parents are already biologists, and my sister, so I try to avoid as much of that. But if there's one thing that we can change for looking at ourselves, what would you suggest that we improve?
The answer is implicit in what I was saying, is that the very first thing that you need to do is to start reading. And you need to read a lot about whatever domain it is that you're working in. Not about how computing works in that domain, but if you're in a bank, working in a bank, read about banking and understand what banking is. Secondly, immediately, as soon as you read 3 or 4 banking books, go and read about business in general, particularly the aspects of business that might have a peripheral attachment to your area. So if you're in banking, I might want to look at international monetary transfers. I mean, it's an interesting area, but it might be marketing, it might be management. I would personally recommend that you go and look at some of the things that business has been writing about adapting to change. their take on how you be agile, how you be a complex adaptive system. So Peter Senge talking about, continual learning would be an example. So I would start with those kinds of things. I would also mandate that you read something, a romance novel, a science fiction novel, a mystery, I don't care what, but something for fun, so that you get the sense of reading as pleasurable. So Alan Kay said that if you don't read for pleasure, you can't read for purpose. And I believe that that's true. So yeah, it would just be, get curious, expand your horizons, and start small and very specific.
You mentioned the crusades against the arts and the crafts by the engineers or the first engineers. I was wondering, what's your take on, what's your opinion on the software craftsmanship movement and their manifesto, and if you have one?
Position on, say it again, what?
The software craftsmanship movement and their manifesto.
Yes, okay. I spoke at the first two software craftsmanship movements, software craftsmanship conferences. And my message to them was what I said earlier. It's not enough. Software craftsmanship movement seems to be almost exclusively focused on learning how to be a really, really great programmer, maybe in multiple languages or multiple language types, procedural and declarative and so on. And then also knowing a whole lot about the history of programming and great examples of programming. So they're borrowing some things from the art world, where if you go to art school, that's what you study masters, you practice, you do it. I mean, there's this constant dialogue with the profession. But they didn't want to go beyond that. They had no interest, again, in the domain space. And it may have changed. The time that I was working with them or spoke to them was, I said the first, at least 5 years, 6 years ago. So the movement may have evolved since then. I don't know for sure. But that's what I told them back at the beginning, was that it's not enough to be great programmers.
Hi, which triggered a question. Did Michelangelo have to be religious to paint in a church?
Say again, I didn't quite.
Did Michelangelo have to be religious to be painting in a church?
Of course not.
Then why do we have to know the domain?
Because if all you are is a great painter, number one, you won't be painting in a church. Number two, nobody is going to get anything out of your paintings. It's going to be pure art. And so we have all seen artists who are technically perfect in their art, but it doesn't say anything to us. It has no power. It doesn't evoke anything of the human. And the same thing, you can build a technically perfect system that runs correctly, has 0 errors, and it still is useless to the people that are supposed to use it. It does nothing for them. So if you want to be a great painter, you don't need to know anything about the domain. If you want to be an effective painter, you do.
Yeah, you have to know what to paint, like that.
Yes. And they painted in churches and they painted religious themes because that's who paid them. So that's another part of it too. You need to know your domain and what your customer wants.
Thanks.
You were mentioning about skill sets and the need to be skilled, but we are in an industry where actually finding good skills is quite difficult. And well, we all have members of our team that are sub-performing and not really at the level that we expect them to be. Nonetheless, they are providing something positive compared to their salary, for example, or whatever. They are producing something, but they will never be able, or from what they look like, able to really reach. So should we maybe work with a smaller team, or just what are keys to decide, yeah, well, we need to let this one go actually because it's harming more than it's bringing. And then come the empathy part of it, which is you work with this guy for a long time, and you see a bit what I want to ask, I hope.
Right. So there's a kind of an inverse relationship between the scope of your problem plus its impenetrability, how little you understand about it, and the team size. So if you've got something that is either really big or something that is really not yet understood, you need a really diverse and therefore a large team. If you're designing, this is true like in the design world. So if I'm designing a logo, I might do it by myself if I was a designer. But if I was trying to create a marketing strategy for a brand new startup company, I would get as big a team as possible. So there's this kind of inverse relationship between the problem and the team. Corollary to that is you're going to have a hard time finding these T-shaped, pie-shaped, broken comb-shaped people. And for that, I'll offer my deepest sincere apology because I've been an academic for 20 years. I've been a professor turning out the recruitment pool for you. And with the exception of the last couple of years, I've done a horrible job. I taught computer science and I taught software engineering. And people that have that kind of background in education are not ready to join your team. The last few years that I was teaching, I started a very different kind of a program, borrowing things from Agile, the just-in-time learning and things of this sort, but it was an apprenticeship program. So people, by the time they had spent 3 years in my program, they had already written 100,000, 200,000 lines of code. They had worked with teams. They had solved problems, as well as learning some of the fundamental background thing. Those kind of people you would want to hire. But most universities aren't turning out that kind of resource.